Is it true that the sum of any two even odd numbers is always going to be even? Well, first thing we should think of when approaching a problem is try and think of some counterexamples. Let's think of the base case. If our two even numbers are 0, so 0 plus 0, that's going to be 0, and 0 is an even number. 2 plus 4, that's going to be 6. 6 is an even number. 2 plus 2, that's 4, that's an even number. 4 plus 6, that's 10, that's an even number. 8 plus 8, that's 16, that's an even number. 12 plus 24, that's 36, that's an even number. Okay, so far I'm struggling, or I can't really think of any counterexamples where this isn't going to be true. So we're going to try and prove it. We're going to assume that it's true. To start, we're going to first write this out as a mathematical statement. So how do we start this? Well, first notice that because we're proving for any two even numbers, for any always means you're proving a for all statement. So let's write that down. For all. And now to make this proof, to make it easier for the reader to understand exactly what we're talking about, we're going to label this even number A, this even number B. So next we say for all A and B that are integers, because even numbers have to be integers, if A and B are even, then A plus B is even. Great, so we have the statement we're actually going to be trying to prove. It's in an if and then form, so we know that this is going to be our P and this is going to be our Q. We're going to suppose P and show that when you do P and you do A plus B, you get something that's even. Now, what does it mean for something to be even? Well, for that, we're going to need the second part to be able to write this proof, a definition of even. So, what is even defined as? An even integer is defined as an x that is an integer such that x is equal to 2k, where k is also an integer. So what does this mean? This means if you think of any even number or any number in general, and you label that as x, when you put it in this equation and you rearrange for k, is k going to be an integer? So a really easy way to check this is, for example, let's do a really common number, 2. 2 is an even number, right? So if we let x equal 2, we put that into the equation, equals 2k. Rearranging for k, we get k is equal to 1. So yes, in this case, 2 is an integer, but if you choose an odd number, for example, 5, and we let it equal to 2k, when we rearrange for k, what we find is k is equal to 5 over 2. And 5 over 2 is not an integer, so 5 is not even. So that's how we're going to use this definition. Okay, now we can begin writing our proof. So we're doing a for all proof, which means we start with the word let. That is the first thing you should think of is the word let. And what do you let? You let this be true. So you say, let A, comma, B be integers. And the second thing we do is, of course, we suppose our P. We're going to say, let there be A and B that are integers and let them both be even, right? So such that A and B are even. Great, we have the first part of our proof, the first sentence. We've supposed P. Next, what should we do? Well, first thing we should do is we should more concretely define our two variables so we can then use them, right? So let's define them in even terms. Let's say then, comma, A is equal to, now I'm going to use different letters than K so you can clearly see my reasoning here. I'm going to say A is equal to 2m and B is equal to 2n. You have to let these equal two different variables. So you can let this equal k, but then this can't be equal k. Because when you let these 2 times something equal the same variable, if these were both m, then what we're saying is A and B are actually the same number. That's what we're saying. So that's why I'm using 2 different letters here. Now remember, we've already defined A and B to be integers, but now we've introduced to the reader 2 more variables, and we need to tell them what those 2 variables are. So immediately after defining and introducing these variables, we have to explain to the reader what they are. So we say, where m, comma, n are also integers. Similar to our definition for even, 2k, k is an integer. Here we have 2m, m is an integer, 2n, n is an integer. Okay, great. Then what do we do? Well, like I said up here, we're going to try this and see if a plus b does in fact equal even, does in fact lead to something that looks like it's in the form of x equals 2k. So let's give that a shot real quick. So we say a plus b is equal to. We then substitute into our equation our definitions of a and b. So we say 2m plus 2n is equal to. Okay, the easy parts have been done so far. This is where the hard part comes in for a lot of questions. For this one, it's pretty straightforward, but for more difficult problems, this is where your pre-calculus kind of like education comes in more handy. So we need to look at this and we need to ask ourselves, is there a way to get this to look something like that so we can say it's even? And with even cases, I would say try and look for the ability to factor out a 2. And in this case, we can factor out a 2, right? So what we can say is this is equal to 2 open bracket m plus n close bracket. Awesome. So this is already a great way, and we've already done over half of our proof. So what you have to notice is m plus n, that's our k, the 2 comes down here, and a plus b is just going to be our x, right? So we've already shown, hey, this is even, right? So what do we have to do? All that's left is to argue that m plus n is the same as k. It's to basically say where m plus n is an integer, right? It has to have the same property as our k. Now remember, the reader won't see any of this stuff apart from maybe the question or the statement we're trying to prove. So it's really important that you make this statement after, again, trying to justify that this is even. Okay, now all that's left is to conclude our statement. So, since a plus b is equal to 2m plus n, where m plus n is an integer, a plus b is even. Therefore, the statement is true. Awesome. We've done it. We've proven that any two even numbers added together is going to be even. Now, if you can't quite see why this logic here works, because this is usually the hard part people struggle with, is they do this and they're like, okay, well, this doesn't look like 2k. Well, you have to recognize this is an integer. Any two integers added together is going to still be an integer. But if you're still struggling with seeing why this is true, you should just say, okay, actually we'll keep this part here. There we go. And we'll say, let m plus n equal k, right? Two integers added together is always going to be an integer. That's typically something you can take for granted in a discrete math course or introductory proofwriting class. So k is also an integer. Remember, we have to define any variable we create. This definition is not part of our proof, so as far as the reader is concerned, it's the first time they're seeing k. K is an integer. So, oh, actually we've already written so we'll say next, a plus b is equal to 2m plus n, which is equal to 2k. And now you write the exact same conclusion. Since a plus b is equal to 2k, where k is an integer, a plus b is even. If you want, you can add another part to the statement saying, by the definition of even. Usually when you're writing a proof, you're assuming the reader already knows the definitions of what you're trying to prove. They already know what even is, the definition. So this part is usually quite useless. But if you want to be super thorough and you're trying to maybe write something for someone who doesn't know a whole lot or might not know these kind of properties, this would be really helpful. And then we just say, therefore, the statement is true. And you can, instead of saying the statement, you can insert into here the statement to, like this statement. You can just re-type that in, but that's just extra work. You get the idea now of how to prove this. So there we go. We've just proven that the sum of any two even numbers is always going to be even.